Have you ever wondered, what is magnetism? How does it influence our life? And how does it connect to the northern lights? Let's start by explaining that there are subatomic particles which form atoms. Atoms are a combination of protons, electrons, and neutrons, which are all examples of subatomic particles. The particles have different charges: positive charge, negative charge, and a neutral charge. The core consists of protons and neutrons, while electrons travel around the core on different energy levels. Atoms make up matter, and known elements are presented in the periodic table. These atoms make up all ordinary matter in the universe, including the Earth. As atomic physics explain, magnetism and magnetic field in ordinary matter originates from two sources, with the movement of charged particles and the electromagnetic moment, which is a property caused by the electrical charge and spin. Electrical field is formed by the charge of the particle, and for the atom, it depends on the arrangement of electrons on different energy bands around its core. Electromagnetic waves result from the behavior of electrical and magnetic field oscillating perpendicular to each other away from its source, traveling through space. Electromagnetic waves carry energy, momentum, and angular momentum. Electromagnetic waves, or radiation, is divided into different spectra depending on the amount of energy they have. These different waves can be seen here and include from left to right with decreasing energy: gamma rays, X-rays, ultraviolet, visible range, infrared, and radio waves. So in the previous video about energy, we discussed the photon. Photon is another subatomic particle. In quantum mechanics, a subatomic particle can be described either as a particle or a wave, and these particles carry energy. Even though photons do not have a charge or interact with each other, their energy and momentum causes the electromagnetic effects. Just to give an example of an electromagnetic wave, let's look at X-ray waves. Most of us are familiar with X-ray imaging performed at the hospital when we break a bone. X-rays are high-energy particles which are absorbed by the Earth's atmosphere. So in order to detect X-rays, it must be measured at a high altitude. The energy source for the X-ray emission is gravity. These sources include neutron stars and black holes when material is falling into a black hole. The infalling gas and dust is then heated by strong gravitational fields. But how can we then use X-rays on Earth for X-ray images and such? X-rays are so called as a German physicist, Wilhelm Röntgen, did not know what this radiation was. X-rays can be made in a vacuum tube that uses high voltage, in other words energy, to accelerate the electrons released by a hot cathode to a high velocity. When these high velocity electrons collide with the anode on the other side, it creates X-rays. Vacuum tube is a tube that has no gas. So when someone goes for an X-ray imaging, these electromagnetic waves are generated and travel through the patient and are detected on the other side, giving us an image of a broken bone. Electromagnetism is one of the four fundamental interactions. The four fundamental interactions of physics include weak and strong interaction, gravity, and electromagnetism. Because of these forces, atoms connect to one another, materials can be formed, devices can be produced, and the human body functions the way it does. Until now, we have discussed the effect from the electrical and magnetic field together. Now, particles have a magnetic dipole moment where an electron generates a magnetic field due to a property of the electron. When there is a majority of unpaired electrons aligned with their spins in the same direction, they produce a magnetic field strong enough to be felt on the macroscopic scale. The Amperian model explains how electrical currents behave the same when they are in a loop. Now, this also explains how the currents in the Earth's core are in a loop, causing our magnetic field. The magnetic field forms in a way that it generates two opposite poles, the north and the south pole. Similar to the charge where north and the south pole attract to one another and the same poles repel. Let's now talk about metals. Metals conduct electricity well as they have free electrons. Free electrons means that their electron can easily be transferred to another atom. When enough energy is provided, electrons move from one atom to the other, creating an electrical current. It is due to this that the Earth has a magnetic field. Earth is a large magnet believed to be generated by dynamics in the outer core of our planet, which is liquid and metallic. The electric currents which are generated there is due to a certain process called geodynamo, and it is that causes the magnetic field. So in our compass, we have one pole of the magnet which is attracted to the other pole, giving us the correct direction. So then how do the polar lights or the auroras light up the sky at night, but usually only in the north and the south hemisphere? Like we have been discussing about electromagnetic radiation and our Earth being a giant magnet, electrically charged particles originating in the sun's corona stream constantly outwards from the sun as the solar wind. This outflowing plasma, intertwined with the solar magnetosphere, forms the interplanetary magnetic field. The solar wind deforms the Earth's magnetosphere, compresses it towards the sun, but drags it outward in an anti-solar direction to form the magnetotail. Most of these high-speed particles are deflected by the magnetic field, but a small percentage leaks through the field's polar cusp. Due to our magnetic field lines, the charged particles collide with atoms in our upper atmosphere around the magnetic poles. When these particles hit atoms high up in our atmosphere, the electrons jump up to another energy level. The electrons do not stay long in this excited state, and when they move back to their original state, they emit certain electromagnetic radiation. This electromagnetic radiation is in the visible wave range, which is the light our eyes can detect. The reason why the northern lights show different colors is because in our atmosphere there are certain types of atoms like oxygen and nitrogen. Because the atoms get different amount of energy, electrons are excited to different levels, returning into their original state later, and this different amount of energy gives the range the electromagnetic radiation will have. When this energy is inside a certain range, our eyes can detect them. As an example, when the northern lights have a green or red color, it is because of oxygen atoms. If the particles hit nitrogen, they emit blue to purple colored light. One other note, other planets which have magnetic field also have polar lights, as can be seen here on Saturn.